So David's result shows that there is something interesting there, right? So computing with classical devices and computing with quantum devices is not quite the same. Can we capitalize on this? Can we use David's idea to construct something even more conspicuous, where we can see the separation of power between quantum computation and classical computation? And the answer is yes, we can. So here is one example that was proposed by Ethan Bernstein and Bernstein-Vazirani. So they consider the following scenario. Imagine that you have a black box. So we are still with this oracle model of computation. And the black box is computing this Boolean function that takes binary strings of length n as input and will just give you as the output either 0 or 1. The promise is that this Boolean function is of this form. So it's a dot x, where a is a fixed binary string of length n, x is your input. So you think about this expression here as an inner product of two binary vectors of length n. So you are promised this, and the task is to evaluate a. You have to find out what is the value of a with as few calls to the oracle as possible. Now, how would you do it in a classical scenario? You can see from this expression that in order to find a, you have to find n bits that define a. So you have to find a1, a2, all the way to an. And the only way to find those values is to try evaluating the function on specific inputs. So for example, if you want to figure out what is a1, you can feed the oracle with a binary string x equal to 1, 0, 0, 0. So that will give you the value of a1 right away. And then a2 will be evaluated when you feed the oracle with a binary string 0, 1, 0, 0, 0, and so on and so forth. So you can see that you need n calls to the oracle in order to be able to answer the question, what is a? How about the quantum case? So the quantum case is described here with this circuit, and as you can see, it only requires one call to the quantum oracle. And the circuit should be familiar to you by now. You look at the top register and you can see quantum interference right away. You can see the Hadamard quantum function evaluation that will generate interesting interference pattern and the Hadamard and the measurement. The second register is important, but it doesn't really require tracking during the evolution of this circuit, simply because it starts in the state 0, -1, ends in state 0, -1, but it has to be there, because when we evaluate the function, we need that register for the phase kickback to introduce phase factors to build an interesting interference pattern here in the first register. So let me step through the execution of this algorithm so that you can see that the end result, the output, is the value of a that can be read bit by bit from the qubits at the output, from all the qubits in the first register. So let me just track the evolution of the first register. The second one, as you can see, is quite trivial, always stays in state 0, -1. So we start the first register in state 0. So that means we prepare all qubits in the first register in state 0. So it's a binary string x equals 0. And then after the Hadamard transform, so we do Hadamard, we have equal superposition of all binary strings x of length n in the first register. So that's the opening of our quantum interference. We prepare all equally weighted superposition of all possible values of x that can be stored in the first register. And then we do quantum function evaluation, so f. And as you know by now, what will happen now is that we will introduce phase factors -1 raised to the power f of x. So the value of the function will determine whether this phase factor is +1 or -1 in front of this binary string x. So let me then perhaps write this more explicitly, because we know what the function is a dot x. So the state of the register here after the function evaluation, so we are now somewhere here, is 1 over square root of 2 to the n, sum over all binary strings of length x, and we have the phase factor minus 1 raised to the power a dot x, and our cat represents the binary string of length n. Okay, now we have interference pattern. Now we are going to close interference. Interference has to happen. We need another Hadamard. So here comes the second Hadamard. After the second Hadamard, and I'm going to use the expression that we discussed when we talk about the Hadamard transform and quantum Fourier transform. And so the normalization factor after multiplying by another 1 over square root of 2 to the n will be now 2 to the n, and then I will have sum over x and y. Both x and y are binary strings of length n, and here I'm going to have minus 1 a dot x and minus 1 y dot x, and that'll be sum over y. And of course, you know, I can now write this as 1 over 2 to the n. Let it be sum over all possible binary strings of length n. I label them as y. And then we have another sum here, sum over x, also binary strings of length n. And let me just write this expression here. You can see I can just rewrite this as minus 1 raised to the power a plus y dot x. Right, so that this is a addition bit by bit. Okay, so now let's look at this expression here. Let's look what we have in front of cat y. So consider two cases here. Consider the case where a is equal to y. When a is equal to y, a plus y is equal to 0, right? So if you do bit by bit addition of two identical binary strings, you get a binary string that is all zeros. Well, in this case, this exponent here is equal to 0, in which case the phase factor here is equal to plus 1, in which case if you add it 2 to the n times, this expression here is equal 2 to the n. So that sort of cancels with 1 over 2 to the n here, and as you can see, for this particular case where a is equal to y, the output is simply a. Now, if on the other hand a is different from y, so that means that this is a binary string which is not equal to 0, so there are some ones somewhere in this binary string. And then you have this sum, so you run through all possible values of x, so all possible binary strings. So when you take the scalar product, it's not so difficult perhaps to see that it will just generate the equal number of zeros and ones. So therefore, this phase factor here will have, this sum will have equal number of plus ones and minus ones. So the whole thing will be just equal to 0, which kind of makes sense because, right, if we get with probability 1 y equal to a at the output, the probability of everything else has to be equal to 0, so which is consistent. So we have 0 as the result of this term here when we evaluate this term for a that is different from y. So that means in this case the whole thing is just 0. So that means that with certainty, with probability equal to 1, what we get at the output is the value of A. So that means that indeed the output, so this thing here, is equal to A, and we can read the binary values of A from the register by bit by bit measurement. So you see, this is actually quite interesting separation. So we have on one side we have classical scenario where we have to make n calls to the oracle, and on the other hand we have quantum scenario that requires only one call to the oracle. Well, of course, one can say, well, this is a quantum oracle, it may be more complicated. Fair enough, it may be more complicated. With oracles anything is possible. And then you say, well, you need also of the order of n gates to implement this Hadamard transform in the quantum interference. So somehow there is some use of resources. It's not only the oracle that we are using here. That's also fair enough. So it would be actually good to have even more spectacular separation. Well, so yeah, let's consider the next step, more spectacular separation, so that if there are any skeptics, they should be convinced that there is a difference, there is more interesting, more conspicuous, more dramatic separation between the classical and the quantum.